All right. Hey, everybody. Greetings. Thanks so much for being here. Greetings. All right. So, yes, hello. This is Open Research Institute's meeting that we talk about FPGA projects at ORI. We do open source digital radio work. What we do in this meeting is we have a roundtable. We'll talk about what we've done over the past week, what we have planned for the next week, and if we have any roadblocks, anything that's kind of blocking our way, you know, being a problem. And then if we need any resources that ORI can help with, or if we can reach out to other people to help you out.
Okay. Well, since last week, we have achieved some new ways of measuring things in Opulent Voice. We added the capability to generate the preamble, which is already in the HDL, but we added support for it to the application code and did some experiments. We found some interesting stuff with that test. Let me show you a screen here if I can. This is the usual kind of plot here, except at the first 20 seconds on the left-hand side of the graph is emitting preamble of the kind that we thought we were going to need. We'll talk about that a little bit more in a bit. But look at that sine wave on the accumulators. They're not supposed to do that. They're not out of control. They're just oscillating, which is a surprising behavior. And then after the preamble is over, it's a while before things settle down and uh, we actually get zero error rate, which is not great result either. So maybe this preamble is not doing what it's supposed to do for us. The other thing we learned how to do um, was to uh, sample more often. So instead of running one whole second, about 54,000 bits, um, and then writing some information down and um, going on to the next second, we're doing it, are able to do it faster than that. And it turns out we can do about 100 per second, which is not as fast as I would like. I'd like to be able to see every bit, but that's completely out of the question with this method of logging um, and writing down the data. But um, we can see a lot more detail anyway. And I am trying to find, there it is, stop share. Um, there's some other graphs that show that, but they don't really show anything very interesting visually, so I won't bother to bring them up on the screen. All I'm able to see from these graphs is that, yes, we're able to generate delays of about 0.01 seconds. We try to generate another magnitude faster than that, and it doesn't because there's just too much other stuff going on in the application code for that to work.
Yeah, it'd probably be good to say that the mechanism here is a timestamp.
Yeah, we had that last week. We've switched to capability of measuring time based on a hardware register provided by the radio hardware. It actually counts CPU cycles rather than samples, so it's not exactly synchronous, but it's a lot better than what we were doing before, where we're just basically running a spin loop at the Linux level. So we're able to measure time pretty accurately. We're just not able to reproduce results at a very, very fine interval.
Yeah,
So
thank you.
100 per second is about what we can do. And since then, we've looked at preambles and different parameters and maybe found some bugs. Matthew can speak to what we've understood about that, and Michelle can also talk about what we've learned about preambles and their generation and their shape. Um, it's very interesting and confusing.
Yes. Now we're learning. So just very briefly, preamble is supposed to help you acquire quicker than the usual traffic. And there are some things, some sort of accepted preambles and some work done about 25 years ago by a variety of folks. And so we think we know what the right data sequence is for the to create the right preamble, and we think we know the theory behind that. So we're just trying to implement those and figure out how to get them to show up correctly over the air. And so I'll hand it over to Matthew because he's got a lot to share about the past week.
All right, thank you. Um, so, in terms of when we were looking at the preambles and the results we were seeing in the lab. I did go back and review this data sequencer, which is kind of a differential encoder, the Massey sequencer, and found that there was an error in the RTL code. So I corrected that, but what's happening now is that it's not demodulating properly. The NCOs seem to be not. There's a frequency offset in the NCOs. I should probably let the simulation run longer and see if it recovers at some point. But basically, I'm getting a bit error rate the entire time. I'm not getting to 0-bit errors. I don't see what the error is in the demodulator. It looks right to me, but I'm still reviewing that as I have time. So that's kind of the open issue from the RTL point of view. And I think, the preambles still bear some further discussion. Because the preambles that we were seeing in the lab, there was a 3-tone version and a 5-tone version. And I think both of those would be problematic for acquisition, but that would be, maybe we can do some more experiments and see. Because with either the 3-tone doesn't have F1 and F2, they're not there. So if you lock, you'd be locking into the wrong frequency. And if you have the 5-tone, you have 3 possible things you could lock to, the correct frequencies, or you'd be offset by I think it's 13.5 kilohertz in one direction or 13.5 the other direction. And so I think the question is, the Massey or the Hodgegard decoder detector is pretty tolerant to phase steps. So maybe, if we lock to one off frequency, it would be okay. But I need to go review the Hodgegard paper again. They tested with a certain phase step, and I don't remember what it was. So I think 13.5 kilohertz is a pretty big step. I don't know that it would be tolerant to that much. So I think there's still some, obviously we have a lot of review to do there. Hopefully we can find something that works well.
Yeah, I think over the past day or so, because I've been ever since we saw this behavior in the lab where we were expecting this preamble to ratchet us in really fast, to synchronize really fast, and when it didn't, so we started digging in to make sure that this is actually right. So we did find out a lot of interesting things when Matthew's talking about 5 tones versus 3 tones. Okay, so this is what we were calling the 5-tone thing. This is actually right according to Fred Harris's slides and his exploration and all the work that he did for the mil spec standard that uses MSK. So about 25 years ago, there was mil standard 181B, and this added multiple minimum shift keying to an existing communication system, military communication system. Fortunately for us, there was a lot of well, I say a lot with an asterisk, a lot for a military standard, but there was plenty of IEEE papers, plenty meaning 2 or 3, that really that clarify this and say, okay, the 11001100 repeating forever, that sort of preamble is the one that you want to use for minimum shift keying. From our experience with regular FSK, MRE FSK, you really want to pick the outer, for your M, if your M is 4, if you have 4 tones, you want to pick the outer 2 and bang, bang, bang between them. And then you'll get a different, you'll get a very clear sort of lighthouse effect on the spectrum. Okay, and this is the 3 tones. So you had 5 tones in the center, now we have 3. So these tones, if you look at the center frequency, that's your IF. And then these particular tones are out at the symbol rate, which is 27 kilohertz. We actually don't want that. That's too far. Where that number 1 is there on the image here, that's the F. Let's see, I think that's F2. So that's our actual frequency that we really want to present to the demodulator as a very clear, hello, we are here. So that 5-tone version actually has that tone there. And that's why it shows up there. Okay, so that number one right there, that's the one that we actually want. Initially, when I looked at this, I was like, oh, those are too close together because in the Simulink model that I have, uh, the tones the tones that I want are actually at the symbol rate at 27 kilohertz. But this is what we're actually doing over the air. So yes, that tone is what we want. We want our Costas loop to ratchet onto that. We want the most energy possible being there. Um, and this is the exact same pattern that shows up in Fred Harris's slide deck from 25 years ago. Fred Harris is a well-known, digital signal processing professor. He's done a huge amount of work and is an IEEE fellow, and this is his area. And just touching base with him briefly, he's like, yes, this is the right pattern you want to see for your preamble. So whatever you can do to get this sort of thing to happen will help you. So a little bit of encouragement in the right direction. This is not an area that's documented terribly well, and there's not a whole lot of like tutorial material about this, but we now have an increasing number of positive affirmations that we're doing it right, and we're going to get good results if we follow down this path. So that's the one. That's the our two frequencies that we're going back and forth between. We want our preamble to really have a lot of energy there to help us acquire quickly. So Paul raised the requirement of let's have an experiment that shows, do we really need a preamble? Because in a paper that Matthew found, it did say that like, wow, your demodulation should be so good that you may not even really need a preamble. So what we're going to do is actually test this. We'll have a preamble when we do have I think we have the right construction, and when we get it reliably happening over the air, we'll be able to test it. So preamble versus no preamble, and then we'll be able to make an informed call on whether or not we need it. I think we probably will.
Yeah.
I think it'll probably help us, but we need to quantify it.
Yeah, I mean, I was just going to make a comment that even in the regular spectrum, when we're not sending a preamble, we're just sending PRBS, the F1 and F2 tones are there that you just can't see them, but they are there, and they're the only tones. Everything else is just spread from the sidebands, from the tone from the regular data. That's why you get the big center lobe.
But Matthew's right. This is why we're able to acquire and to demodulate, and we've been doing this for weeks and months with no preamble whatsoever. Because those are the two tones that are in the signal.
Yeah. So I mean, so the F1 and F2 are there. You just can't see them. The Debuta demodulator actually does a squaring of the signal, and you can see the tones pop up significantly. But they're there, and so but you can't see them right in this graph. They're underneath or right at the the top of the tones are probably right at the envelope of this.
Yeah. You can
Yeah.
if you look at the lower in the spectrograph, you actually can see like the two vertical lines. So you can see them come out if you have this view, if you have a pantograph kind of view. But you're right, like if you look up at the top in the spectral sort of curve, you're not going to really see them.
Yeah.
Thank you.
So the modulator will lock to these, right? Because they're the only tones effectively that are there.
Right. Yeah, we're just trying to see if do we get an advantage with a preamble? Like, can we quantify the advantage if it's like
exactly
if it's a significant amount of time? Like, if we get some traction, then great, we'll include it. But if it doesn't really help us that much, then
right. So I mean, the problem with the PRBS is you might get three, some string of zeros or effectively F1s and some of F2s. So the two loops aren't getting equal time in terms of locking, right? So it may take longer for the loops to lock. Whereas if we had an appropriate preamble, then they would lock much faster, because you're getting two F1s, two F2s back and forth.
Yeah. No. Anything else you have to add, Matthew?
I don't think so. I guess we kind of keep coming back to this. I think I'll just add it to the hardware. Not sure, it takes some change to the application, but we could get a sample by sample resolution in terms of logging by streaming. I could basically take all these parameters that we're reading from the registers and stream them into the receive off over the EXI bus. So they would go directly into memory, and then software could process them and generate these plots at a sample per sample resolution. So I think, it's not very difficult in the hardware. It's just a matter of, constructing a little frame with all that data. We already have the data in the hardware, of course, and then streaming that, instead of streaming recovered or detected data, this will be a kind of a diagnostic mode where we're streaming the NCO adjustments, the error values, all that type of stuff. And again, we'd be able to get sample level resolution if we did that.
That sounds like a pretty powerful validation method.
So I think that would be, figuring out what's happening in the demodulator with the correct sequencer, and then if we can add this diagnostic mode. I think those would be probably the two things I'd focus on this week.
Okay. Wow. Thank you so much. This is exciting. And I have plenty to write about. I'll just share very quickly. So there's at least 6 or 7 different ways to look at minimum shift keying signals. And the one that I do in Simulink is offset QPSK. And it turns out this is not necessarily automatically compatible with the way the Massey decoder or encoder or the Massey Hodgart encoder decoder work. You actually have to make sure that you agree on things like where you start in terms of phase, and which is the cosine and sine, because you can get some weird results. So now, over the past week, I found out this is why that the decoder in Simulink is kind of totally not working exactly right. It sort of works. Sometimes it doesn't. And so I think over the next week, this might actually take a big step forward. So that was a whole bunch of learning. There's a paper that Matthew found that is really neat, and it talks about MSK, minimum shift keying, and the different viewpoints or points of view that you can have in terms of how to describe it and how to define it. I took this paper as all of these views were equivalent, but they're not. There's lots of implementation details, and it turns out I was doing it wrong. So I've cleaned up my Simulink, and hopefully that will help make some good confirmation models. And our goal is to describe this in a way where people coming after us don't have to do all the stuff that we had to do in order to understand it and to implement it and to get it accessible to people that want to use it, because this is a fantastic mode. It has lots to offer. So I see Aaron's joined us. Aaron, I know that you're limited in time, and if you would like to have the floor here, please go ahead.
Sure. Sorry, I was a little late today. But in this last week, I switched over to implementing the MSK modem using OpenCPI. I've got it transmitting, and I'll get with on Slack. But I had a couple questions on computing the right F1, F2 register values if the sample rate changed. I understand that the Pluto right now is at 6144 megahertz. And I wanted to run it at 3072. And I had some calculation. I made derived some calculations using some of the register values that I found on GitHub. But I'll get with the team to figure out exactly which ones to use. As far as what I'm planning on doing this coming week is trying to replicate the success on the Pluto SDR that you guys have been describing for the last couple of weeks. So I have a known working modem that I can compare it to. And that's all I have.
Well, thank you. That's a lot. Yeah, Matthew, do you have anything you want to?
I was just going to say, we can discuss on Slack, of course, but one key thing here is that in the Pluto right now, it's at 61.44, but we're decimating basically. Not decimating in a proper sense. We're just throwing away 24 of 25 samples to get the effective sample rate down to about 2.5 megahertz. So if you're running the Pluto at 31 or 32-ish megasamples per second, you want to drop that decimation value down to maybe 12 or 13 or something like that to get that lower effective sample rate. And then once that's done, I think, but I think the NCOs are programmed the same anyway. There's
Mhm.
another decimation inside the NCOs, but the NCOs themselves run at the full rate. So, okay, so the NCOs are probably running at 32. So we do need to change the calculation for the NCOs. It's fairly simple. So we can, yeah, of course, discuss that in Slack.
Okay. Thanks, Matthew.
Yeah, thank you so much. This is really
Let's
neat stuff. Oh, go ahead.
maybe we could take a beat to talk about that decimation um, value. The value of 25 we have to do in the HDL, but if we chose a different number like 24, I think we could do it in the Pluto um, or in the radio. It's got some built-in decimation capabilities, and that would save us a lot, I think. And um, well, yeah, that's worth considering.
Yeah, absolutely. I think, I mean, right now we're just throwing them away, which is kind of fine, but not fine, in terms of if there's no filtering ahead of time. Um, so the value is programmable in the FPGA. We could certainly try different values, and if there's one that was compatible with the uh, hardware decimation, then yeah, we could certainly switch to that. I mean, yeah, I mean, we have a lot of flexibility in terms of how we configure the demodulator and given the hardware that's around it. But ideally, not just ideally, but we do need some sort of filtering. Um, we don't have that currently, but in our test setup, there's really no um, extraneous signals getting in, right? So we're not over the air with an antenna; everything's cabled, so we're not getting whatever might be ambient signals around that could be aliasing into our passband. But eventually, when we do over the air experiments, then we absolutely would need, I think, a filter ahead of the throwing away the samples or a proper decimation filter, so that we don't alias other things in.
Yeah, that's well worth talking about. I think the way that we're doing it is the right way to do it in order to figure out the right way to do it, and then to get a handle on it. But we've started to kind of get a little more familiar with there's a MATLAB um, Pluto aimed application that lets you design your filters and tells you which exact hardware resource that's already on there you could use. And we are so not far away from that. It may take a little bit of adjustment, so it may change a little bit of the filtering. Um, but as I think as this will be actually an easy transition. No, it might be jinxing it a little bit to say that, but when we move from handling it all ourselves in the HDL and then moving to letting the Pluto hardware, the existing Pluto and the hardware handle it, I think this will be a good experience. Go ahead, Paul.
Oh, I just wanted to show the block diagram of the 9361. Those HB1, HB2, HB3, uh, they exist in the transmitter and in the receiver. In the transmitter, they're interpolation, of course, and have filtering. In the receiver, they're just they're filtering and then decimation. So that stuff's all built in. There's an FIR to take care of the front end filtering, all built in. So that's the thing I was talking about.
Yes. Yeah, we're not using that right now, but what we've done is, you know, in our efforts to kind of define what our signal needs to do and all the things that we've implemented, some of this can be offloaded to the existing hardware. So,
Yeah, it's not in the FPGA though. It's in the radio chip. It's um, no
right,
cost against our other resources.
right, maybe an improvement. So we'll do that. Now, when we talk about our design going to even other radios and other chips or other implementations, then this particular thing uh, comes up again as like a consideration. So if you're going to move off to say another analog devices design, you'll see these same filters there, and you will be able to take advantage of them. They might be a little bit different, bigger, smaller, whatever. But a totally different design, you're still going to have to handle this function. So um, we should
In
probably,
certain, I was going to say certain front end devices may not have the filters, right? So we might need those in the hardware anyway.
right.
But in resource constrained devices like the 7010, yeah, if we can move it off to the front end, that's really good.
Yeah, I think you said it better than I could have. I think I'm like, you'll still have to handle this. So, so we don't want to just delete it from our design. We want to communicate why we had it in there and to say if you need it in your implementation. So this is sort of a tricky communications problem when it comes to publishing an open source design. And this is where Matthew's leadership here has, I think, really made a difference. So if you have a modem modular approach, where you have clearly defined the functions and the things that you're doing in your design, and you make it very clear, why are you decimating? And, then somebody that's taking that design can then make an informed decision about what to offload to existing hardware if that exists, or what they have to still take care of. So I think we're in good shape. We just need to be vigilant and make sure that we communicate this particular decision, because it makes a big difference in terms of being able to fit into other hardware. But in terms of like our efforts to make this really usable on a very popular SDR, the Pluto, things are looking good here. We may be able to leverage the existing hardware, free up resources, and um, win in the end. So thank you to everybody involved. Yeah, thank you to everybody. I think we'll have a really good week in the lab, and we're talking about, I don't know, there's like several papers that, several articles and papers and lots of documentation to do. So we'll be mindful of that and try to communicate it all forward. We have another newsletter coming out today, tomorrow, very, very soon. So our March newsletter. So a lot of this will be in there. So again, thank you to everybody involved.